Hello everyone and welcome back to the channel. Happy Halloween. As you can see, I've gotten in the spirit myself. I've pulled out one of my many onesies in the collection. No, I am not a furry. And today we're going to be talking about ZooKeeper. Now, in some senses, they call me a bit of a zookeeper myself because I'd be letting these dogs out all over the internet. But in other senses, I am not a coordination service. So let's go ahead and talk about what ZooKeeper is and how it works, and enjoy the video. Alrighty, so let's go ahead and talk about ZooKeeper. I'm going to try and keep this onesie on the whole time. I may very well overheat and have to take it off mid-video, but I'm going to do my best and we'll see how that goes for us. So ZooKeeper is a paper out of Yahoo. I know, right? Crazy. They were relevant maybe 10 years ago, which just goes to show you this isn't the newest paper. It's probably about 10 years old. But for some reason, I couldn't find an exact date on it, which is why I omitted it here. But yeah, I'd estimate about 10 years old. So basically, ZooKeeper is a coordination system insofar as it is mainly supposed to be used for application metadata and configuration. Things like where servers live, what's running, what's not, environment variables, stuff like that. And so ZooKeeper is going to be supporting linearizable writes, but at the same time, it does not support strong consistency, which is interesting because I think maybe I've often misquoted myself, or I've said that it kind of does, but the truth is, even though it runs on top of a consensus algorithm, the reads themselves are not necessarily strongly consistent. So we can do reads and notifications from follower replicas. Those are completely local reads. You don't have to do them from a quorum. And then in addition, you can basically build all of these kind of coordination primitives, or what ZooKeeper calls recipes, on top of it. Because of the fact that we have these linearizable writes, we can take advantage of those guarantees and build more powerful applications off of that. And then notably, they do a lot of comparing themselves to Chubby, specifically on the performance front. So I do think if you're watching this video, I do have another one about Chubby from like 2 months ago. I'd recommend checking that out because there's a lot of shared terminology between the two. Because ZooKeeper really does create itself with Chubby in mind and, trying to kind of improve upon the pitfalls there. Cool. So even though I did say go watch the Chubby video, for those of you who have already watched it or are just too lazy, let me just give a really quick recap. Chubby is also a coordination service, right? It's also for application configuration, but it's also a locking service, specifically for coarse-grained distributed locking. So in Chubby, they make very extensive use of caching. Basically, they want every single piece of data to be auto-cached in every single client that's interested in it so that you don't have to read from Chubby all the time and it heavily decreases the load. That being said, Chubby also wants strong consistency. And so if we want strong consistency, we need to basically say to every single client that's caching a value, if I'm writing that particular value, I now have to go invalidate every single client cache before that write actually succeeds. And so because of the fact that you can have very long tail latencies there, right? One particular slow client that doesn't respond to your invalidation request can make writes take forever. So basically they have some sort of session timeout in Chubby where the session is basically how often you're heart beating with Chubby or the leader of Chubby. And so if the session itself gets invalidated because, there hasn't been a heartbeat for a while, then that, the cache is going to get flushed, right? Chubby's client library will basically flush the cache for you. And so they can say, okay, well, at worst, I know that after this timeout for the session, a write is always going to go through. But in practice, it seems like a lot of the time when you have many Chubby clients and one of them is going to be slow to respond, every single time that you write, you pretty much have to wait for the duration of the timeout of the session. And so that is going to be pretty bad. And so it's going to make write throughput very slow. On the contrary, what ZooKeeper chooses to do is implement wait-free data structures, which really just means write normally. So let's talk about a quick overview of ZooKeeper, just so I can say that I did it and no one lambasts me in the comments. Basically, it is itself a distributed key value store. Like I mentioned, it's mainly used for application metadata. The intention here is not to make a ton of application writes to this thing. You're not going to get great throughput. We'll discuss why that is, but the gist is distributed consensus. And so the idea is that very, very similar to Chubby, same exact API for users, generally speaking, with the subtraction of a couple features, actually. But basically, data is stored in all of these nodes, or Z nodes, and each one is effectively represented by some sort of file path. So in this case, if we have some path Jordan/girlfriends, we can create a bunch of nodes under that. So, Corinna Koff is my girlfriend, Megan Fox is my girlfriend, Michelle Obama, she gets thrown in there. And all of these are the data associated with every single one of these nodes. And so interestingly, whereas Chubby supports kind of a lock node out of the box, ZooKeeper does not. We just have this concept of data nodes. So you can write data at a particular path, And so another thing or another operation that they support is also reading that data, but also doing a compare and set operation, right? So I can basically say, edit node if version equals 4. And that kind of ensures that you're doing atomic operations and that data hasn't changed between the time that you're trying to write it and now. And that particular primitive right there, that compare and set operation, allows us to build quite a bit off of it. Cool. So basically the idea of ZooKeeper is that we're going to be doing wait-free writes. Now hopefully at this point, if you've been following along with this series, you're fairly familiar with the concept of how writes and a consensus algorithm are going to work. ZooKeeper is going to be using a single leader consensus approach, and so this is going to be using their algorithm ZAB. They call it atomic broadcast, which to my understanding just basically means you're making linearizable writes, so that's all good and well. And basically the concept here is you've got your leader, you've got a couple of followers, and ideally we want to be using quorums to ensure that all writes are durable. And so the leader, or basically the followers as well, they're going to keep in-memory state of all the nodes, right? That like node path hierarchy. And then additionally, they also have this commit log, or you can even call it a write-ahead log because technically it serves as both. And that is really what ZAB is going to be replicating between the leaders and the follower nodes. And so you can see that it is possible, because we only care about getting a quorum of nodes to commit a write at one time, that a follower can lag a little bit behind. Now the reason it's important that a follower can lag a little bit behind is because ZooKeeper actually allows local reads from any replica. Now, note that in the majority of consensus-based setups, this is not a thing you can do because it pretty much allows you to read stale data, right? So in the majority of consensus setups in like Paxos or even Raft, something like that, your options basically to ensure that you're reading up-to-date data are you can read from a majority of the nodes because data is going to exist on the majority of the nodes, or at least the most up-to-date state is, or you can actually read from the Paxos or Raft leader, depending on the implementation. And so reading from the majority is going to be slow. You're basically subject to the slowest of those nodes to respond. And then similarly, reading from the leader, it should be faster because you only have to reach out to one node. But at the same time, one, this isn't very scalable. As we continue to add more clients, this just puts a lot more load on the leader, and that's something that's bad if we want to support tens of thousands of clients. And also it's going to be slowing down our writes, right? Because now you're just using extra CPU devoted to returning all of this read data. And it's going to slow down our writes because all the writes also have to go through the leader, and the leader is already basically a bottleneck in this situation. So what ZooKeeper is going to allow us to do instead is basically, like I said, take local reads from every single replica, even if it's behind. And so what this basically means is that data can be stale. Now, it's worth noting that one thing that ZooKeeper does support is every single read to a local replica will basically give you the last known ID in the transaction log or the commit log back to you. So in the event that you do switch replicas that you're reading from, you can make sure to basically wait out until you see an entry or a read that is a higher number than your last read value. And that way, at least your reads are going forward in time, right? They're monotonic as opposed to potentially jumping backwards in time, and that would be very bad. Cool. And then additionally, another nice feature that ZooKeeper supports is something called a watch, and this is very important for some of the algorithms we're going to discuss later in this video. But think of a watch as basically when I read a value, I can say, okay, I'm reading the value, but also I'm going to set a watch on this. So if the data changes for some reason, please come back to me and tell me that the data changed, and then I can read it again and set another watch. And so that's going to be very, very useful for some of the algorithms that we'll talk about in a bit. Similarly, that's called a data watch, but there's also like a children watch. So, if you have some path /a, you can basically set up a watch that will tell you when a new child node is added under /a. Now, keep in mind, this isn't delivering you the data itself. It's just saying, hey, something has changed, go load it yourself. In theory, I guess this is an optimization one, so you don't have to deliver every single piece of data. You can kind of batch watches if there have been many writes in one area. But also now you're sending a lot less data over the network, and the client really has to decide itself whether it wants to make another read and actually fetch all the data. Cool. One more keyword that I'm going to talk about as a ZooKeeper feature is the sync keyword. So keep in mind that, like I mentioned, you can have stale reads from any follower, right? So imagine this is our follower. We're a client over here. We're trying to read from it, and we're trying to read this key X. However, now we're going to go ahead and use the sync equals true. So basically what sync is going to do is it's going to ensure that when you do make this read from the follower, that any outstanding writes that haven't yet fully been committed by the leader are going to be flushed out to this follower, and then you'll read it. So basically the sync keyword first goes to the follower. It then gets sent over here to our leader. It basically gets batched in with any batched writes on the leader that they're trying to commit or maybe have been prepared or something like that. And then eventually when this data flows back to the follower, keep in mind the sync keyword is only going to the particular follower that initiated the sync, not all followers. So it's not like a majority write. It's not treated as a full transaction, but it basically gets batched in with the packets that are being sent to this follower. The follower receives that sync keyword. It says, oh, hello, here's my sync. Let me go return whatever in-memory state I have back to the user, and as far as we know, that's about as up-to-date as it gets at the moment. Cool, so that is going to allow us to basically ensure that we flushed out all outstanding writes on the leader. Now, of course, it's not going to be as fast, right? There's a lot more latency to this operation, but sometimes you need these types of guarantees. Cool. A couple other ZooKeeper features that I'm going to quickly cover because they are important for the later part of this video. One is this concept of a persistent versus an ephemeral node. So basically, persistent nodes are going to be written once and they'll stay around forever until they're explicitly deleted. Ephemeral nodes are basically deleted when the session that creates them terminates. So let's say I'm a client and I create some node and then I crash. Eventually my heartbeats are going to stop sending and the node that I created, that ephemeral node, is going to go away. And so this is an option whenever I create a node. There's also a concept, which I haven't written here, called the sequential node. So this is basically saying, okay, let's say we have some path A that we're going to write under. Rather than giving the child of A an explicit name, we're just going to assign a monotonically increasing sequence number. So the first sequential node would be A/1, the second one would be A/2, on and on and on, and ZooKeeper handles that for you. So you don't have to be like, ooh, if there's a node 3 already, then we'll be node 4. Well, that could be problematic because someone else might write node 4 and you're not going to know about it in time. So yeah, just another convenience feature there. You can also, like I mentioned just before, you can get and register watches on the children of a node. So, when there's a child node added under a particular path, you can get notified of that. And then also pretty much everything is ordered in ZooKeeper. So the ZooKeeper writes themselves are ordered via ZAB and that kind of atomic broadcast protocol, but also every single notification that a client receives and every single, operation that a client sends is also ordered. That's just done via TCP because, let's say you were to get notifications in the wrong order as they were coming in, that could be problematic as well. Like you wouldn't want to get your watch notifications in the wrong order because maybe you have some watch notification that tells you, hey, something is ready to go, and then, hey, here's the new data that you can read as a result of it's ready to go, or hey, here's the new data, and oh, hey, now it's ready to go. You can just have bad consistency guarantees based off of that. So it's very important that all notifications are also delivered in order. Anyways, the gist is, let me stop rambling. We can go ahead and use these features to build more functionality with ZooKeeper. And so we're going to go through now a few different algorithms, or not necessarily algorithms, but basically just like high-level ways that you can use ZooKeeper to do more complicated shit than just, write a bunch of nodes and read a bunch of nodes. So the first one is just configuration management. Imagine you have a bunch of like environment variables or something like that, or variables in general that everyone needs to know in your application. And when they change, everyone needs to be notified. Super simple. You create one data node where everyone, has the hard-coded path. In this case, we'll just call it app/configuration. Any client can write to it. Everyone else is just read it and establishes watch. And so when this configuration changes, you get notified, you go ahead and read it again. Now, of course, note that, again, this is like eventually consistent, right? There's no way for you to basically guarantee that like you're making a read of this configuration with its most up-to-date state the moment after the client writes it. But for something like configuration, a lot of the time it doesn't matter. Even if it's like you're hitting the wrong server now, you're going to have timeouts for a couple of seconds, you're going to get your watch, and then you're going to be good to go. So a lot of the times it's not a huge deal, and basically I guess the operating philosophy here was that Chubby was a little bit over the top in that sense, and if you do really need such strong consistency guarantees, you can still build them with ZooKeeper. Okay, another one to do is going to be group membership and service discovery. So it's worth noting that we actually saw this in play last week in our Kafka paper. This is pretty much exactly what they did. So imagine you've got a few different servers, right? A few different partitions or something, and we need to know the address of all of them so that we can reach out to the appropriate one. Basically, on startup, every single one of these guys should register themselves with ZooKeeper as an ephemeral node. And so we've got app/A, app/B, app/C. Maybe they got their host and their port in there, just so as a client I know where to actually send my requests to, right? I can, create some sort of client object and then send HTTP requests over to them. And so this guy, if I'm a client, we're sitting here, we basically establish a watch for new children of app slash, because I don't know the names of these servers beforehand. Maybe I do, maybe we could use a sequential node, but the point is, if I don't know the names of the servers because, maybe they're just registering under some random path, this is basically going to allow me to know when there is a new child added. Then I can basically ls this directory. Ls just means show me all the children node. And then I can see the new child, and then I can actually say, oh, look at C, it just came up. Let me go ahead and read that data because I didn't see that before. So hopefully this makes sense as to how you would do that pretty simply. All right, moving on. We're going to talk about establishing locks with ZooKeeper. So the first thing that we're going to do is talk about how you would do locking naively in ZooKeeper, because that one's pretty easy for the most part. Basically, imagine we've got two clients. They both want to grab a lock. Well, since all writes in ZooKeeper are ordered, it's pretty simple to just say, all right, why don't we create a node called /lock? Let's make it ephemeral so that if I go down, the lock actually gets released. And then over here, this guy can do the same exact thing. He's also going to try and create a node /lock that's ephemeral. Obviously, only one of them is going to succeed because they're both doing this around the same time and all writes are ordered. So let's say our guy on the left succeeds. Okay, that's fine. I didn't grab the lock for now on the right. But what I will do is I'll now read that path for a node that exists, and I'm going to set a watch on it so that way if this guy either goes down or if he just releases the lock and deletes the node, I know that the lock is now available and I can go ahead and grab it myself on the right. Hopefully that makes sense. The problem with this is that it should really easily lead to a thundering herd, right? If a bunch of our clients want the lock at the same exact time, maybe I've got another guy here, I've got another guy here. Everyone is getting notified around the same time when that lock gets released, and now everyone is going to be sending a ton of operations to ZooKeeper at the same time. So if there are n clients, every single time the lock is released, there's going to be n watches that are being registered, and there's going to be n write attempts, which is not good. That's going to put a lot of extra load in our system. So what can we do that's better than that? Well, basically, the idea now is that in order to avoid a thundering herd, rather than just trying to grab one individual node /lock, what we can do is every single attempt to grab a lock is going to create a node in the lock path with an increasing sequence number. And remember, we can do this very easily with sequential nodes. So basically, the first attempt to grab a lock by client A is going to create lock /1, and maybe the second attempt is going to create lock /2, and the third is going to create lock /3, the fourth is going to create lock /4. So basically, if you're a client, okay, let's say I have lock /1. Since I am the sequential node under the lock path with the lowest sequence number, I currently am holding the lock. If I relinquish it because, my ephemeral node gets deleted or I just give it up, well, that's good. That just means I release the lock. Now, the nice thing is that in this algorithm, basically what you do is when you create your node, your lock node, you set a watch on just one other node. And the node that you set your watch on is the one that is basically the lowest remaining node under you. So right now, lock /2 is watching lock /1, and when it gets deleted, it gives up its lock. Now lock /2 is holding the lock, right? And it's saying, okay, now I am holding the lock. Now let's say at this time, lock /2 is still holding the lock, it's still doing some sort of work, and the client that's responsible for the node holding lock /3 says, ooh, I'm gonna go ahead and crash, right? So this guy crashes. When we crash, it's an ephemeral node, right? So all of a sudden this node gets deleted. And so when this node gets deleted, keep in mind that lock /4 was watching lock /3. It's going to say, oh, wait a second, lock /3 is deleted. What's the next lowest node under me? Oop, now I'm watching lock /2. And I'll give up my watch on lock /3 because that one doesn't exist anymore. Sorry, so we're doing lock /2 over here. And then now that we're doing lock /2, let's say that the node with number 2 says, all right, I'm done doing my work as well. I give up the lock. Now lock /4 is going to say, ooh, I see that lock /2 has gotten deleted and given up the lock. Now I'm holding the lock. So this is really, really nice because of the fact that every single node is only waiting on one other node at a time. And so when one node gets deleted or it grabs the lock and removes it, only one other node, whoever made the next claim for the lock, is going to be the one to have first priority at getting it, right? There's no concept of a thundering herd here. Now, actually, what's really cool about this concept is this is your typical, simple lock, but you can also implement ReaderWriter Locks this way. So let's go ahead and show that off. It's actually a very, very similar concept. So basically, in the same idea, right, we've got this guy over here, this writer lock, or sorry, this is a reader lock if I have /r. Basically, the idea is right now, because it's the lowest one, it's holding the lock. So keep in mind that for reader-writer locks, you can have many readers having the lock at once, but you can only have one writer having the lock at once. So let's say, someone else comes in and tries to grab a writer lock over here at sequential number 2. So now what they're going to do is actually, as you can see here, they're going to put a watch on the node under them, right? All writer locks are going to set watches on, the closest node under them. However, and the same is over here, right? If someone else tries to make a writer lock claim, they're going to be watching writer lock 2. However, if you're making a reader lock claim, this is where things get interesting. You actually watch the closest writer lock under you. So in this case, as you can see, for reader lock 5 and for reader lock 4, they're basically both setting a watch on writer node 3. The reason being that, I don't really care when reader 4 is created or deleted if I'm reader 5, because of the fact that we can both be holding the lock at the same time. So the only thing that is a barrier to me at time number 5 from grabbing the lock is actually this guy over here at time number 3. And so we basically have this kind of recursive setup where, okay, let's go through it. Let's say lock R1 goes down, or it gives up the lock because it's reading on its own. Okay, now this guy is going to register that. It's going to say, I'm holding the lock. Okay, maybe it does its work and it deletes the lock. Now this guy registers itself because it was watching that and say, now I have the lock. Let's say it finishes. Both this guy and this guy were watching node number 3 to see when it gets deleted, to check if they can go ahead and claim the lock. And when they do, they can both see, oh, okay, we're good to claim this. And because they're both readers, it's shared access to the lock. Right? We can have 2 readers accessing the lock at the same time. We just can't have 2 writers accessing the lock at the same time. And you can't have a reader and a writer accessing the lock at the same time. Cool. The last thing that I want to talk about, the last recipe, is called a double barrier. So this is something that I personally haven't actually really heard of too much in distributed systems, but it's probably because I'm just not that much of a beast yet, and I'm trying to get there. I guess the gist is we want to be synchronizing communication between many different processes at once, right? So everyone starts at the same time, so they enter the barrier. Everyone ends at the same time, they exit the barrier, and then they can go back to doing what they were doing before. So the barrier kind of, gets activated or crossed when enough processes have registered themselves with it. And then when all the processes that have registered have, said, okay, I'm complete with doing my work, then everyone can exit the barrier and carry on. Cool. So basically how we're going to do this is everyone is going to create a node in the same path, right? Maybe we have some barrier path, barrier slash. And so everyone is going to then set a watch on some sort of arbitrary ready node, right? We can tell all the clients beforehand what this node is going to be. So maybe barrier slash ready is the node. And so if I'm node A, what I'm going to do is I'm going to create a barrier slash A. I'm going to then check, okay, have we reached the threshold to say that we're ready to begin our computation or not? And then if not, I'm going to do nothing. I'm just going to set a watch on this barrier slash ready node. And then I'm just going to hold on until enough processes ready themselves. So eventually, maybe we'll get B and C registering themselves. And at C, we say, okay, I think we have enough processes to, start our computation. What C is going to do is it's actually going to create this barrier slash ready node. You can register watches on nodes that don't even exist yet, as long as you know the path they'll be created at. So C, when it says, okay, I see now that we have 3 children under this barrier path, is going to create the barrier slash ready node. A is going to realize that, and then everyone's going to begin their computation. Now, it's pretty much the same exact thing when ending the computation. When you end your computation, you go ahead and delete your node under the barrier path. And if you see that you're the last node to be deleted, then you also go and delete the slash ready node. Everyone else is still subscribed to notifications on the barrier slash ready node. And when they see it's deleted, they know the whole process is done and they can move on with the barrier. So I did go ahead and do a little shitty visualization through this. I'll walk through it one more time, but hopefully this makes it super concrete for everyone. Basically, the really nice thing about this is, rather than having to rely on counting the number of these processes every single time, right? Because what we could do is we could have A and C also register a child watch on the barrier path. But that would be bad because it means that every single process that enters the barrier, we now have to notify every single process total. So that's going to be an n squared number of notifications. This way, we have an n number of notifications because everyone just subscribes to the /ready node, and so it's going to be a lot more efficient. Cool. So basically the idea here is, let's say we have client A, it starts up, it's ready to do computation, it creates barrier/A. Got client B, it does the same exact thing, barrier/B over here. Same thing with client C, barrier/C. Barrier/C is going to do a read of the children in the barrier, and it's going to say, okay, we've reached all 3 of ours, I think we're ready to write the ready node. So it goes to ZooKeeper and it says, okay, I'm going to create barrier/ready. Now, barrier/ready is going to be watched by A and B already, and so they're going to be notified in step 5 and step 6 that they can go ahead and start their computation. Now, after some amount of time, all 3 of these nodes are going to be doing their computations, and they're going to finish. So in step 7, maybe node C finishes first, it deletes its node over here. Maybe in step 8, node A is going to finish its computation, so it deletes its node. Keep in mind, they're still saying, okay, well, I see there are other children at the barrier, in the barrier path, so I'm not going to do anything just yet. And then finally, node B is going to come along, delete this, and say, ooh, I see that I'm the last child in this path. Now I'm going to have to go ahead and also, in step 10, delete the barrier/ready node. So once we do that, everyone receives their watch notifications on that node, basically saying, hey, this entire thing is done. We can go ahead and move on. Cool. Another quick thing that I want to talk about is this concept of replica snapshotting. So even though it's really nice to have a write-ahead log because it determines whether or not things are truly durable, we all know that, if we crash and we start back up, you can replay the entries of the write-ahead log in order to get back to your previous state. However, of course, if there are a lot of entries in the write-ahead log, as I'm sure there are because there are just many writes to ZooKeeper over time, this is going to take a really long time, and we want to be able to recover a little bit faster than that. So typically what we'll see in systems is they'll take a sort of snapshot and associate it with somewhere, one position in a write-ahead log. That way when you recover, all you have to really do is you take the point in the write-ahead log that it corresponds to, restore the snapshot, and replay all the entries from that point in the write-ahead log. So the one, prohibitive thing here is that snapshotting can be expensive, right? Because if you want to take a consistent snapshot with that exact point in the write-ahead log, you have to make sure that your in-memory state is not modified while you're taking the snapshot. So even though you can add to the write-ahead log, you can't actually make any changes in memory and show the data to clients. However, ZooKeeper has a way of basically avoiding all of this locking as it goes ahead and takes a snapshot. There is still node-level atomicity, but I guess the gist here is that across nodes, ZooKeeper is not going to lock its state. So it's going to start the snapshot at one particular entry in the log, and then it's not going to lock anything. So as the snapshot is being taken, we may see writes, basically if the snapshot starts at log entry X, we may contain writes from later timestamps. We could have a write from X plus 2, X plus 1, X plus 7. There's not really any guarantee, but we know that it may contain later writes because, let's say I'm reading this tree right here. So I start my snapshot in this very state. I've read all 3 of these nodes, and right as I'm about to complete my snapshot, this guy here gets added. And, all of a sudden now we have an extra write in our snapshot. Basically, the gist is that the only way this is going to work for us to not double apply log entries is for all of them to be completely idempotent, right? Everything in our write-ahead log has to be an idempotent operation, or else we might, double apply some data. Let's say we had some operation like x equals x plus 1. If we applied that once in our snapshot and then we applied it once again in the write-ahead log, now all of a sudden we have an x equals x plus 2, and that would be bad. So basically what ZooKeeper does to avoid this is it has some, kind of piece of its application called the request processor. And so every single incoming request out of ZooKeeper, the request processor will effectively transform it based on the current state and the request from the client to ensure that it is an idempotent operation in the log. So for example, let's say I'm a client and I submit some operation like, oh, x is equal to x plus 1. Clearly this is not an idempotent operation, right? Because you can do that 5 times and now all of a sudden you have x equals x plus 5. What we want is one that you can do 5 times and you get the same result regardless. So let's imagine the current value of x is 6. Effectively what the request processor would do is in our replication log, rather than showing x equals x plus 1, we would just write x equals 7. Because if I apply x equals 7 twice, x is still 7. Okay, quick couple of notes about the performance of ZooKeeper before we get into our conclusion here. So there are 2 basically main advantages over Chubby on the performance front, And I guess it just offers a lot more flexibility because it doesn't force you to kind of opt into this strong consistency and these cache invalidations that Chubby does. Number one is that you're not waiting during your writes, right? You don't have to wait for a session timeout every single time, which is pretty huge in terms of write throughput. Number two is that you can do local reads on follower replicas. So as you are actually scaling things out and you're getting tons of read requests, because generally speaking, ZooKeeper is serving a disproportionately higher amount of reads than it is writes, we want to be able to serve them from as many places as possible. And a lot of the time, it's okay if that's slightly stale. Like even with perfect strong consistency, there's no guarantee that right after you make a write, you're going to go ahead and read the database and see that you have your updated value. So in some ways, it's kind of fine if you have eventual consistency here, as long as you know that every kind of replica that's a little bit behind is going to converge, which we do because of the consensus algorithm. Okay, another thing to note is just in general choosing the cluster size. I guess this is true for all of these kind of like Paxos or Raft or Zab based implementations. But the gist is if we have more replicas, well, actually it's not necessarily true for them. If we have more replicas, at least in the case of ZooKeeper, because we serve these local reads, we will get better read throughput. However, we're definitely going to get worse write throughput because writes have to go to a majority of nodes. And as a result, basically we are kind of subject to the slowest node out of these groups. And then finally, we're also able to partition ZooKeeper. So, if you have a bunch of disjoint applications or a bunch of disjoint writes, partitioning makes a lot of sense here. And that is going to allow us to get both better write throughput as well as better read throughput as well, because now you just have more nodes to read from. Cool, let's go ahead and do a quick conclusion here before I wrap things up and get myself to the gym. Basically, the gist is if we relax our consistency guarantees, we can achieve much better performance than Chubby. Now, that's not to say that ZooKeeper doesn't take a lot from Chubby. I mean, the API looks very, very similar. ZooKeeper doesn't actually implement locks explicitly, but basically by having Zab and having a system where you can achieve linearizable writes, you can basically do all of these cool coordination primitives on top of ZooKeeper that you might need in a variety of distributed computing applications. And so like we mentioned, you could do things like a lock, like a ReaderWriter lock, double barrier, service discovery. And so ZooKeeper ends up being a very powerful tool, even though it looks very simple from a very high level view. Anyways, guys, I hope you enjoyed this video. I think it was very cool for me as well because I didn't really understand in the past what kind of the stark differences were between Chubby and ZooKeeper. I honestly was kind of under the impression that ZooKeeper was just like an open source implementation of Chubby, which as you can see is clearly not the case. And hopefully this will lead me to say less bullshit about it in my future videos. Anyways, guys, enjoy your Halloween and have a nice weekend.